Kindly write your name in the chat box for your attendance. And allow me to share my screen now. Okay, so we're now on not just one particular physical system, but several systems arranged in series. But in this case, we will only limit the series systems to be identical. So when we speak of series systems, series of liquid level systems, or it could be series of mixing systems or something like that. But in our case here, they will be all identical systems that we're going to arrange in series. Now, the arrangement in series of these physical systems can either come in two forms. So we have the interacting and the non-interacting connection. So for those who have already read in advance or scanned through their book, they know what I'm talking about. So let's go first to the simple of the two, the simplest of the two, and that's the non-interacting system. So the systems are still arranged in series, but they are said to be non-interacting. So you may wonder why non-interacting? So the outflow in this case from the previous tank, when we speak of the liquid level system, is discharged directly into the atmosphere before it's being spilled into the next tank or before it is being introduced on the succeeding tank. Now, in this case, we say that the level in the first tank is dependent on the resistance. So flow through R1 depends only on the level. Now, variation in the level of the succeeding tank, let's say if we have tanks 1 and 2, the level in tank 2 then does not affect the transient response of the previous tank. So in this case, now we're looking into how will the level of tank 2 affect the level in tank 1. In this case, it will not affect whatsoever the level in tank 1. Now, if you look into the illustration for this type of system, you have a simple liquid level system here, which has two tanks. Now, the flow rate to linear resistance 1 is labeled as Q1. For the flow rate flowing through resistance 2 is labeled as Q sub 2. You have the levels as H sub 1 and H sub 2 for tanks 1 and 2 respectively. And the volumetric flow rate to tank 1 is Q. So we're going to check how will the behavior of the level in each of these tanks. And so by the way, we don't only limit it to 2, but in this case, just for illustration purposes, we only had arranged 2 tanks in series acting in a non-interacting fashion. So as I've said, we're going to check how will the levels in tanks 1 and 2 be affected by changes in the volumetric flow rate of or to the first tank. Okay, so how will be H1 when Q will be changed in a step function of magnitude 10, or how would be the level in tank 2 be affected if this one will be changing in sinusoidal fashion or something like that. Okay, now if we have several tanks, since we have only 2 here in the illustration, if we have several tanks in series, let me go to that particular slide. So it would be something like this. So this is how we simply illustrate several tanks reacting or having non-interacting relationship between them. So you are going to multiply each of the transfer functions of each tank. So if you multiply the transfer function of tank 1 to tank 2, you are getting actually the overall transfer function of the two tanks. If you're going to multiply the transfer functions of tank 1 to tank n, so you're actually getting the overall transfer function of the n series of tanks arranged in non-interacting fashion. So this symbol tells you, so this is not summation, but if you never see this symbol, it's like you're doing summation, but instead of adding, you're multiplying. You're multiplying individual transfer functions. That way you'll get the overall transfer function of your tank in series, having non-interaction relationship. Now, in terms of the overall transfer function of these two tanks that I have shown to you, and if we will follow this particular rule in finding the overall transfer function, this is the overall transfer function of your system. So H sub 2 of S over Q of S. In this case, you are trying to determine the effect of changes in the volumetric flow rate of the liquid to tank 1 to the level of the liquid in tank 2. So you're multiplying the transfer functions of the two tanks. If it is the volumetric outflow through the resistance in tank 2, relationship to changes in volumetric flow rate of the liquid to tank 1, it would be something like this. So this is only true, class. This is only true if your tanks are identical or if tau 1 is equal to tau 2. By the way, this should not be the symbol, but I think my system here cannot, I don't have the tau when I made this particular slide. So this should be tau 1 and tau 2. So this one is for identical systems, two tanks arranged in series in non-interacting fashion. Okay. And this is our non-interacting tanks arranged in series and how we find their overall transfer function. Now, if we're going to plot in one graph the relationship to the response of this particular tanks arranged in non-interacting fashion to the corresponding numbers that are connected in series. Let's say, for example, you only have one tank. This is your response. So you have, it's just like you have a standalone liquid level system for a step change. By the way, this is for a step change in the volumetric inflow. If you have two tanks, this is how it is. If you have 3, you have 4. And I think based on the pattern that you are seeing here, if you're going to add more, there will be, your curve will even be more, shall I say, or mathematically your curve will have less and less slope. It will, this is for the standalone liquid level tank in series. And the term that is being used in your book is the response is said to be sluggish. You attach more and more tanks in your series, the response is sluggish. Let's say, for example, we'll just compare for a T over tau value for these 4 different scenarios. In here, you have 4 tanks. In here, you have 3 tanks, 2 tanks, and 1 tank. The response reaches its maximum of 0.8 for this time over tau value of 2 when it's only 1 tank that you have. But given the same time of, let's say, T over tau value, which is 2, if you have 2 tanks, it only reaches 0.6 of its ultimate, where this one reaches 0.8. In here, for the 3, even lesser. So in here, you can more or less have 0.3, 0.3233. And in here, you have around 1.75 or 0.175. So the more and more systems or the more and more tanks you attach to your system, the response is getting, shall I say, slower or sluggish, as the term that is used by your book. So that's it. So if you have 1 tank, it reaches 0.8 at the same time, but the more you add to it, it becomes really sluggish, which is actually, class, very self-explanatory. The more tanks you add to your system, it will take a lot of time for the last item or for the last unit in your system to feel the changes in the volumetric inflow that is happening to the first tank, because it has to pass through several tanks that were arranged in series. So it's the same thing when we have several tanks arranged in series. So allow me to illustrate to you how you will derive the transfer function of this particular type of system. By the way, for this one, okay? Now, if you have a liquid level system in this case, I will just go to our board. That way I will have, okay, class, excuse me. Can't seem to see it here. Okay. Let's share again. Okay, so let's say we only have 2 tanks in our series. And for tank 1, of course, we have this one as our mass balance, if you recall, for a liquid level system. What enters tank 1 is Q, and what leaves tank 1 is Q1. Okay, I hope you saw it. If you can still recall, just here. Let me show to you again the tanks in series. Okay, so I can show to you how it's derived. Okay, so we have Q1 leaving, Q entering. This is the level. This is the linear resistance. Okay, that's for our tank 1. So I'll go back to our board. Okay, so this is our material balance. Accumulation is equal to rate entering and rate leaving. Okay, now this is specifically since we have level in tank 1, so I will label this as PH1. And on the right side, I'd like to express this Q1 as discussed in liquid level system as H1 over R. Okay, now then you have here dH1 dt. So now I will only relate one variable to another level to changes in Q. Then you will evaluate this at steady state. So this will be 0, and you will have Qs, or rather Q sub S, H sub 1S over R. Now specifically, since I'm talking about tank 1, this should be R1 as well. And then I can do subtraction here, and I will have A, or if we'll have specifically this one labeled as A1, we can do that because we're talking of tank 1. But if our system is identical, your A1 and your A2 will just be the same. So you will have now dH1 dt equal to Q minus Q sub S minus, so I'll take the 1 over R1 here, and I'll have H sub 1 minus H sub 1 of S. I have already illustrated the concept of the deviation variables in the first part of this module. So I'll go directly to changing the small h1 to d capital H1 dt. And I will now change Q minus QS to capital Q, the deviation variable. And I will have 1 over R1 times H1 as for in replacement to the deviation for the deviation variable equivalent to h sub 1 minus h sub 1s. Now, if we take the Laplace of this expression, we will have a1s h sub 1s minus that's for this one. Okay, the first derivative will have s h sub 1 of s, and then the next to that would be a sub 1 h sub 1 0 equal to this will simply have an S, and this will also have an S. So you have Q of S minus 1 over R1 H sub 1 of S. Now we know that there won't be any felt change at time equal to 0 to the level of the liquid in tank 1. So this term becomes 0. And I'd like to transfer this one here. So I have A1 S H sub 1 of S plus 1 over R1 H sub 1 of S being equal to Q of S. Now I can factor the H sub 1 of S here, and you will have A1S plus 1 over R1 equal to Q of S. Then we'll have our output H sub 1 of S over this one I'll transfer here, Q of S being equal to this one I'll simplify. So I will have now, if I'll simplify this one, this would be A1 R1S plus 1 over R1. This thing alone. So if I would transfer it in here, what would be transferred in here? I'll just write here. So that would be R1 over okay, if this thing is placed under here, so you will have R1 in the numerator and your A1, oh sorry, and your A1 R1 product is your tau 1 actually. So I'll just change this one right away. So this is your tau 1S plus 1. So this is for your first tank, the liquid level behavior as to changes in the volumetric flow rate to tank 1. What about tank 2? So if we'll have tank 2, so the accumulation in tank 2 would be represented in this manner will be equivalent to the amount of fluid that is entering the tank per unit time minus the amount that is leaving. So the same as what we did. So you have A2 dH2 dt. This one now will be changed to H1 over R1, and this one will be changed to H2 over R2. The relationship between volumetric flow rate and level. Okay, we have used or we have encountered this in the introduction to this module on physical systems, the liquid level system. Now, we'll try to transfer this H2 in here, but before that, of course, just like what we do when we determine transfer functions, always evaluate at steady state. So H1S over R1 minus H2S, H sub 2S over R2, then subtract, then you will have A2 dH2 dt equal to, I'll have here 1 over R1, and I will have H1 minus H1S minus 1 over R2, you'll have here H2 minus H2S. Again, in deviation variables, I'd like to have here E2 d capital H sub 2 dt equal to 1 over R1 times H sub 1 capital minus 1 over R2 times capital H sub 2. Then I'm ready to take Laplace transform because they are in division form. So A2 S H sub 2 of S minus A2 H sub 2 of 0 is equal to 1 over R1 H sub 1 of S minus 1 over R2 H sub 2 of S. Now this came from this one in which we have performed the Laplace transformation of. Okay, so this is it now. Again, just like the first tank, at time 0, there's no felt change in the level of tank 2. So that would be 0. I'd like to place it in here. So I have H2, or rather A sub 2S. And if this one is transferred here, that would be 1 over R2. It's plus already. Then I'm factoring out the H sub 2 of S. Okay, that's my left side, and left with 1 over R1 H sub 1 of S on the right. Now, since I want output to input again for my transfer function, so level 2 in relation to changes in level 1, that would be, in this case, 1 over R1 all over. If I will simplify this and place the simplified form here, I will have A2R2S plus 1 over R2. Okay, now this A2 R2 is equal to tau 2. Now then we'll have I'll transfer this R2 in here. So H sub 2 of S over H sub 1 of S is equal to, I'll transfer it here. I will have R sub 2 over R sub 1. Then my denominator class would be tau 2s plus 1. This is, let's say, our equation 2. And this is our equation 1. The purpose I'm showing to you the derivation is so that you will know how to derive later on when you do your own thing, especially if you're given a different system. This is not our equation 1. I'm looking for the transfer function that I'm going to use together with equation 2. Wait, probably it's on the previous slide. This one. So this is our equation 1. Okay? Now it says in the slide that you are to multiply the transfer functions of each of your systems if they are arranged in non-interacting fashion. So we will do just that to get the what? The overall transfer function of your system. So I'll have here, if you consider 1 and 2, with the goal of getting an H2 of S over Q of S, that would be, so our first transfer function is H of 1 of S over Q of S. I'll go back to that later. And our second transfer function is H sub 2 of S over H sub 1 of S. This is actually our equation 2. The equation we just worked out a few minutes ago. And this is the one that was labeled as equation 1. This one. So we have here R1 over tau 1S, tau sub 1S plus 1. So I will copy it in here. So you have here an R1 over tau sub 1S plus 1 for this. And for the H2 of S over H sub 1 of S, that would be this one. Okay, R2 over R1 over tau 2S plus 1. Okay, this is our equation 2 here. So what happens is the R1s cancel each other. So true to what was shown to you a while ago, for the overall transfer function of your system, wait Juliana, you'll have R2 over tau 1S plus 1 over tau sub 2S plus 1. If your systems are identical class, then we can say that your tau 1 is equal to tau 2. The areas are the same. So this can even be simplified into R sub 2 over tau. So that would be tau S plus 1 squared. So this is your overall transfer function for a two-tank system having non-interacting relationship. Okay? H sub 2 of S over Q of S is equal to R sub 2 divided by the square of tau S plus 1. Now, for this morning, for a change, let me go back to the slide. You will derive the transfer function for an interacting system. So what is the interacting system in here? So this time, the flow through a resistance in between tanks is dependent on what? So on the difference of the level of the first tank and the level of the second tank. So flow through the linear resistance, the first linear resistance now depends on both H1 and H2. So unlike the previous wherein the level of the previous tank is not affected by the changes in the level of the next tank, this one it does. Okay, So variation in the level of the succeeding tank affects the transient response of the previous. So the response of the previous is now dependent on the response of the succeeding tank. Now I will illustrate this to you here in the illustration for for interacting system. Now, it's not anymore like the non-interacting tank wherein the flow rate here is dispensed into the atmosphere and then introduced, to the next tank in this fashion. This time your R1 linear resistance 1 will now consider both, rather it's a constant, but rather the volumetric flow rate to linear resistance 1 will be a function of H1 and H2. And what is that? So we say that your Q1 class is equal to H sub 1 minus H sub 2 over R sub 1. Yes. Okay, so we say that the volumetric flow rate through resistance 1 is now being affected by these two. Whereas you see this one, it's not having another tank in here. It dispenses into the atmosphere. We just say that your Q sub 2 is still equal to H sub 2 over R sub 2. So in here, what is changing is this. Your scenario would still be changes in the, or how will changes in the volumetric flow rate to tank 1 affect the levels in tanks 1 and 2, but with a change relationship on the flow rate of the liquid leaving or passing through linear resistance 1. Okay, so you have this. Okay, now your goal class is, I'll show to you the, let me clear. Your goal is to get this transfer function. So for your tanks, your two tank system arranged in interacting fashion will have a quite different transfer function than the non-interacting tank. So this is your transfer function for such a system. If we're going to change the numerator in our transfer function here, level to volumetric flow rate through linear resistance 2, then this would be your corresponding overall transfer function, provided that you have an identical tank. Areas 1 and 2 are the same for your interacting tanks. So for the remaining 25 minutes, we'll see each other after 5 minutes. You are to derive the transfer function of these interacting tanks. Okay, because what is placed in the book is rather a direct form of the overall transfer function. Okay, the process is not really in detail. So I'd like you to determine the overall transfer function or derive the overall transfer function for this system. I'll get back to you after 15 to 20 minutes, okay? If you have any questions, feel free to drop me a question in here. I'm just in here. Are you going well with what you're doing there? It's quite long when you derive the transfer function of the interacting system, but the process class is still the same. However, you will change Q1. Let me go back to the board. Okay, here in tank 1, if this is your original DE, and for non-interacting tanks, you only have H1 over R1, you change this one to H1 minus H2 over R1. So in your first DE that you will take the Laplace transform of course, after you have written everything in deviation form, you cannot write the transfer function in this form, but rather you will have one long equation that relates H1 to Q, and then you have another term here which is H1 and H2 that are being subtracted. Now, same thing with tank 2. When you're here in tank 2, this Q1 here will be H1 minus H2 over R1. Just process the algebra, then you will still get the transfer function like this. However, of course, the transfer function will not be as simple as this one. Okay, I will go back to our slide. Your transfer function would be something like this. I only require you this one. You are to submit your work in the Google Drive. One member of the group will submit the derivation in the Google Drive for the first sit work this term. That's for the group. I'll stop sharing. If you're still there, can you give me a thumbs up sign? Okay. Why the others does not have a thumbs up sign? Nika, are you there? Nika. Okay. Can you do it, the derivation? Are you done? Message, not yet though. Thank you, Emilio. You have around 12 minutes to finish. It's better that you derive it because at times class, when I give a quiz, it's already a combination of let's say one part is non-interacting, the other part is interacting. So if you don't know how to derive on your own and you're just simply relying on the ready-made derived transfer function for a two-tank system only, non-interacting and interacting, then you won't know later on when you're given a different system. And there are actually problems in there's a problem in Kauhanor wherein you have a combination of systems. So but remember the author only gave you separate systems, so you need now combine what you learned in the derivation of the transfer function of the two different systems. I've mentioned about the quiz or the exam. Let's say, for example, you're given a combination system, two tanks non-interacting, then attached to another two tanks interacting. Since you know already the transfer function of the non-interacting tank, you need not derive it from the very beginning or from top down. So actually you are allowed to directly substitute the transfer function of the two tanks that are interacting in that are non-interacting to the transfer function also of the two tanks that are interacting. So you combine the two. Let's see what would be the corresponding transfer function, the overall transfer function that you'll be getting. But you are allowed to do that, not that you're going to start from top using the individual, shall I say, mass balance of each of your tanks and then come up, let's say, for the overall transfer function of your system. If it's, let's say, a four-tank system, okay, a combination. So that would be very long. You are allowed to use the derived equation in that case. Who has done already? Who is done already, rather? Who is done? What group is done already? Checking on Canvas, there are 8 groups. So anybody from the group of Aliana, are you done?
Second tank pa lang, miss. Nabudlayan ko, miss, sa first tank.
Ang mag-derive ka mo sa first, wala man, hindi nyo pag-i-derive gani ang transfer functions. Ang first tank, kay hindi nyo na siya ma-derive, kay tungod nga may Q ka mo, may H1 kag H2. So what as what I'm saying a while ago, it's just like one long equation which has 3 variables to relate. You have Q, you have H1 and H2. Mas hapos actually ang iya sang tank 2 kay nga aman duha lang na dang ma-relate mo. You have H1 and H2 because your Q1 and your Q2 are all in terms of H1 and H2. Sige, be. What about the group of Raymond? Aribato, are you done? Okay, or anyone in the group of Raymond? Emilio. Emilio was saying it's not done a while ago. It's not yet done. Emilio, Mika, or let's say, what about the group of Awit? Salido, Tupas, Hava. Okay, not yet done, Miss. Not yet done. What about SOC, your group SOC? Agbuya, Aledro, Tiasis, Ogerio. Okay. Okay. What about Sarah, Katrina, Meryl, and Jules?
Nang sa akon, miss, naka na ang si tangkuan kag tangto, pero kuha pa, miss, ang H2S over QS, miss.
Lawig-lawig na siya kat nga part. What you're going to do is, since you will be relating H2 to Q, kinahanglan you think of a way that you will eliminate H1 in the 2 equations. What should be left is just Q and H2. So ang tanan na ninyo nga H1, dulaon dapat. What about the group of Jobern, Jacel, even the group of Kenneth, the group of Joshua.
Hello, Doc. Gad-derive pa lang ko, Doc.
Rewrite. Sige,
Nakabudla. Ay, gad-derive pa lang. Wala pa, Doc.
derive pa. Sige, since it's almost time, this is what you're going to do, Whatever it is that you have done, whether ang itsura, sinado, kuris-kuris lang, I want it submitted in the Google Drive by 10:35. Okay, I want what was done in the last 20-25 minutes of the class. Okay, for the group, just one submission for the group, whether it's finished or unfinished. I just want to see what you did in your derivation for your seat work here. Okay, Iskilaw ay intindihon ko basta makita ko nga may ginobra. Okay, you need to submit that in the Google Drive. I will download by 10:35. So I give you 3 minutes to do that. Okay, so later this afternoon, you work out your problem sets. That way you will have less time to consume when you prepare for your exam next week. Okay. Sige, so it's 10:30 already, class. Bye for now. I'll be seeing you Thursday for our feedbacking. I will now end this meeting. Bye.